Yeah, there's a lot of
Okay. So I mentioned yesterday that we're headed towards, we need to do rotational dynamics. We got to get there. And but we're going to utilize what we know about energy to get there. And it's going to take a while to get there. It's not going to be till tomorrow that we fully do the rotational dynamics. So as a step in that direction, we want to first consider rotational energy. And we're going to consider a rigid body here, okay, with a fixed axis of rotation. So that's what this is supposed to represent. And you can imagine it to be a collection. It could be a collection of point particles, but if it's not, if it's continuous, you know, like something like this, you can imagine it to be a collection of, you can split it up, right? Typical calculus idea. It's a collection of particles. Each particle is in general going to have some kinetic energy, and we know what that is. So here's one particle right here, one tiny little particle. It's some it has mass mi. It's some distance from the axis of rotation. And remember, that distance, of course, is the perpendicular distance to the axis. That's why I drew this square. This is supposed to be a perspective. This puts things out towards you like this. So that distance is important because the kinetic energy, the total kinetic energy, is going to be the sum of all these little kinetic energies due to all these particles. So the ith one here it's going to be 1/2 the mass times the square of the speed of this little particle here, right? The speed, remember what it is? It's omega times r. It's proportional to the distance. We talked about that yesterday. So, remember this? Oops, right there? Right. So for a rigid rotating body here, the speed of a particle is proportional to the distance. So we substitute that expression, v is equal to omega r, into here. We square it, and now omega is a constant. Every point here has the same omega. It has the same rotational rate, right? This is a rigid body. So we don't have an ion there. It's characteristic of the entire body. So we can factor it out of the sum. Now, you normally think you want to factor it this way. Well, I'm factoring it this way for a reason. Look at the form of this. 1/2 something involving the inertia times omega squared. So that's how we write it. 1/2. We called all of this capital I, and it's called the moment of inertia of the body about this axis, about that particular axis. And what the moment of inertia is, you can see it from here, you have to sum up all the mass elements and multiply by each mass element you multiply by the square of its distance to the axis of rotation. So, does this look familiar? This should look familiar. It looks a lot like the linear result, right? So it's easy to remember. So for straight line, for translational motion, the instantaneous kinetic energy of a particle is 1/2 the mass times the square of the velocity. It's the same thing for rotation of a rigid body, except we have to use the analog of the mass, which is the moment of inertia here. And we have to use the analog of the velocity, which is obviously going to be the angular omega, the angular velocity. So it's easy to remember this. Now you'll notice here that this doesn't just involve the mass, it involves the distance the mass is to the axis. And that's got to be true, because this is contributing us some kinetic energy to the total value. If I doubled r for the same omega, what's going to happen to its contribution to the energy? It's moving twice as fast. It's going to contribute 4 times as much energy as it does here if you double that. So distances are important here. Now, any questions so far? So that's the basic formula. Now, often we're dealing with continuous bodies, okay, like this. And in that case, to calculate, and we're going to do several calculations today, to calculate the moment of inertia, the sum here becomes an integral. So an integral over all these little mass elements. So the mi becomes dm, a little bit of mass, and you need to multiply by the square of the distance of that little mass from the axis of rotation, and then integrate over all of them, okay? So this may look strange to you, but it's perfectly legitimate, and it's very physical. You know, it's just a little bit of mass times the square of its distance. To convert it to an integral that we can do, we want to get rid of this mass. We want to put it in terms of coordinates, right? A little bit of volume. So we do that with the density. The density is the mass per unit volume. So we'll go through some examples. We'll go through several examples of this. But just formally here in the general case, the density at the location of this little mass here, there's going to be some density. And by definition, it's the mass divided by a little bit of volume. So I can substitute for dm here. I can substitute rho dv. So that's what I've done here. So now we've got something. Once you know what rho is as a function of r, now you've got an integral. This is a little bit of volume. In Cartesian coordinates, it's dx, dy, dz. You know, now it's reduced to integral calculus. Now, in this class, I think all of our densities are going to be constant. Like here, for example, right? Density of aluminum. So once we realize that it's a constant, it can come outside the integral. And then we have to integrate r squared over a little bit of volume elements. So that's what we'll be doing. We're going to do that very soon. Before I go to the next page, any questions so far? This is pretty straightforward. It's a big advantage using energy. We're going to be able to get at the dynamics using energy. Okay, so what about this? We're going to spend some time now on this quantity called the moment of inertia. Okay, we're going to calculate it in special cases. And all introductory mechanics books, you can look up moments of inertia of different objects and different axes of rotation. So let's go through. Let's start with the simplest possible case, and that's a single point mass. So this is a mass here. It's some distance r from an axis of rotation, and it's small compared to this distance. It's really a point, okay? From a practical perspective, when we say it's a point, what we mean is its diameter here, the characteristic length of this body, the radius or the diameter, is small compared to that distance. So we can approximate it as a point. So to help see this, you may want to imagine a massless rod, a rigid rod of negligible mass connecting the axis to the mass here, and that this is going around like that. Okay? It's got a moment of inertia. What is it? It follows immediately from the definition. Each particle contributes its mass times the square of the distance. So we're done. The moment of inertia of a point about some axis, a point mass, is the value of that mass times the square of the distance. It comes immediately from here. Okay? Oops. So next up is two identical point masses. Okay, you can see I just copied and pasted this and then edited it, right? So now we're going to imagine two identical point masses separated by some distance that we'll call L, and we're going to choose the axis to be at the midpoint here. So this is a dumbbell. So you can imagine, and again we can imagine that we have this massless rigid rod connecting the two. So this thing could be spinning like that, right? With these point masses on the end. So now, what's the moment of inertia? Well, we got to add, this is going to contribute this, the mass times the square of the distance. This is going to contribute the same. So we just get twice. However, you always want to be careful here. in terms of the dimension that's usually used here, the distance between here, this distance is not L, it's L over 2. So when I do the sum here, when I look at one mass, I'm going to get the mass times L over 2 squared, and then I'm going to double it because I have the identical one over there. So in the end, in terms of this length L here and the individual masses, this is what we get. You always have to be careful with these expressions. You know, if you just looked at this, you might think this is L. That's not wrong. You might think that's the total mass. Nope. The total mass is 2m. You could express it in terms of the total mass. You know, you make this a capital M, you'd have to have, then it would be 1/4. So you always have to be careful here of what the lengths and the masses are. Now, whenever we specify a moment of inertia of a body, it doesn't just depend upon the body, it depends upon the axis, because all the distances have to be measured from the axis of rotation, obviously, right? So you need to specify the axis. And here's a good example. What's the moment of inertia of the dumbbell about an axis here? Okay, what does this contribute? Nothing, exactly. It's got no rotational inertia, which means you look at it and it spins. You don't have to do anything. Right? It has no moment of inertia, it doesn't contribute. So it's going to be, well, ml squared. Is that what we got here? No, we have 1/2 ml squared. So they're different. So in general, it's going to be different. You move along here. So you always want to be aware of that. Okay, next up, and we're getting successively more complicated here, is the hoop. And we're going to take the axis of rotation to be about the center of the hoop. And this is a thin hoop, which means its thickness here is small compared to its radius. So for this continuous body, we're going to switch to capital M here. This is commonly done. That's the total mass of the hoop. So what's the moment of inertia of a hoop? It's actually easy. You can just write it down immediately. Why can you write it down immediately? Each mass element is the same distance from the axis. So it's just mr squared. Each mass element contributes the same, so I'm just going to sum up all of the masses, and I get the capital M, the mass of the hoop. So these, you know, you don't have to look this up. You can just rederive this. You know, these simple things like this, they follow immediately from the definition of the moment of inertia. Okay, now the rod. So now we have a rod here. This has mass. It's a uniform rod. What does uniform mean? I'm sorry?
Same density throughout.
Yes, right. Uniform means that the density, the mass per unit volume, is the same here. Okay, and like I said, I'm pretty sure that's all we're going to be considering in this class. Okay. Now, some of you may have done non-uniform density problems in calculus. You may, you know, because like I've told you before, these center of mass calculations and these they're commonly done in integral calculus courses. So I was talking to a mathematics professor yesterday, and he was looking at all the demos we do, and I said, some of these demos relate to calculus. You know, when you need to integrate to find the moment of inertia. So I told him he needs to talk to me about it. Come by the demo room, demo lab.
Calculus, not more variable.
Yeah, I think demos are a good thing. You know, they help. You know? But you know, they do take time and effort, and that's a lot of professors just aren't interested in that. Okay, so what do we have here? We've got this rod. We're going to choose the axis. The natural, you know, common choice is the center here. So it's got some moment of inertia. And oh, by the way, what that means is, if you know where we're headed with this. If I try to rotate this thing, it presents an inertia. I can feel it's got inertia, okay? Because when I push on this thing, when I push on it here, it's resisting what I'm trying to do to it. It's got inertia. And this is the quantification of that. Okay, so here we go. This is it's a thin rod too. We'll talk about a thick rod in a moment. This is thin. This distance is small compared to this distance. That's what we mean by thin. So here it is. It's a one-dimensional. Here it is from a physicist's point of view with the dm. We got to get rid of the dm because we got to do an integral, right? We use the linear mass, the mass per unit length here. That's the appropriate density to use here because it's a one-dimensional problem. That's often called lambda. So it's dm dx. Lambda is the total mass divided by the total length because it's uniform. And it'll also be given by this, and it's the total mass divided by the total length. So I replace dm here with lambda dx. And lambda's constant, so it comes outside. We'll just leave it there for now. And now everybody can do the integral of x squared, right? It's 1/3 x cubed, and then you need to evaluate between the limits. Now it's common here to make life a little easier and less likely to make a mistake. We know that when we do this integral from here to here, whatever I get here, I've got to get here by symmetry. So it's good here. You're less likely to make a mistake, and it makes it a little bit more enjoyable, I think, to instead of doing this integral, I'm going to double the integral from 0 to L over 2. So whatever contribution this is to the moment of inertia, this has to contribute the same. So that's the physical statement here. You can also see it mathematically. This is a symmetric. The integrand here is symmetric in x. It's the same for a minus x values as a plus value. You know, we're finding the area under a parabola, and it's going to be symmetric. So we'll double the integral from x equals 0 to lambda over 2. So I got the 1/3 x cubed. I evaluated upper limit, lower limit. No contribution to the lower limit because it's 0. And we get this result. And no one remembers this. Okay? I didn't know. I look at it and I go, what is that? The reason is it's much better to get rid of the lambda. The lambda we use temporarily in order to do the calculation. But now we're going to go back and substitute the total mass divided by the total length. And now we get the standard result, 1/12 ml squared. And even this is not that standard. All right? And the reason we will mention later on in the lecture, you'll see why, and I'll remind you about this. But anyway, this is the result for a uniform thin rod rotating about its center. That's the inertia, the moment of inertia. Now, what if we had a thick rod? So here's the top view. Here's the axis coming out at you like this, right? And this is going to have some moment of inertia. Let me put a dashed line here just to help. So it's going to have some total mass m. It's going to be some length here. Is its moment of inertia going to be 1/12 ml squared? What do you think? You have to think here. This is
Yes.
Okay, somebody said yes, which is obviously wrong.
Yeah. I'm used to that.
You expected that, huh? Yeah, here's the idea. It's actually very simple, but if you don't see it, then you're totally confused, right? Let's consider a little mass element here. Now, before, we took this to be down here, right? And we took this length. Its actual length here is bigger. You see it? To find the moment of inertia, we don't take this little mass, this mi here, and multiply by this distance. We got to multiply by this distance. So the answer is the moment of inertia is going to be greater. And if you want to know the precise thing, you can look it up. The standard thing, it's going to be in all introductory mechanics books. And it'll involve this dimension here. You'll need to know this dimension. You need to know that length, or the total thickness, whatever. Yeah?
So what makes that different, I guess, then from the thin rod? Couldn't you do that with the thin rod then as well?
Oh. You can, I'm not sure if this is what you're asking. By knowing the thin rod, you can calculate this. This is really, you can think of this as a superposition of a bunch of thin rods. But you've got to notice here that this thin rod, the axis is not there. You've got to take that into account. I don't know if that's what you were asking, but that's what you triggered me on.
Okay. Okay.
Yeah. You got to do, look, the bottom line is to get this without looking it up, okay? Oh, and incidentally, I'm sure you can find this on the internet. Just type in moments of inertia. You'll get more than you want. Okay? So if we were going to do this, we would have to integrate. And one way to do it, there are different ways, is to view this as a collection of thin rods, of infinitesimal masses, and integrate over all those. That's one way to do it. Okay, next. So the rod is useful. We're going to get use out of this, and we're also going to get use out of a disk. And you can imagine why. Because in the next chapter, we're going to be rolling things. We're going to look at axes that aren't fixed. And the main case we're going to consider is going to be an axis moving parallel to itself, like something rolling down an incline. We'll also talk about tops and gyroscopes, but that gets a little complicated. We'll just talk a little bit about that. So the disk is going to be an important object for us. So we're going to take it to be a uniform disk. Right? It's not loaded. Okay, it's got this, its density is constant here. Its mass per unit volume is constant. Total mass m. It's got some radius, and we're going to find the moment of inertia about the axis of symmetry right here. So this is now a double integral. We have a little bit of mass here, and I got to integrate over all little masses, and it looks to me like a double integral. So you can treat it that way. Well, you can treat it from a purely mathematical point of view, and you can do that. But it's not fun, I don't think, and you're likely to make a mistake. Okay, so here's what we do. This is a standard trick, and they do this in calculus, I think. We're going to split the double integral into, is there somebody dying out there? We're going to split the double integral into two single integrals. So what do I mean by that? So this is, I think it's probably done in calculus, but this is definitely how physicists look at it. I can tell you that. Here's the top view of the disk. I see a little, we're free to choose the element of mass, anything we want to be. Okay, I've been writing as a little cube or a little square like that. Here, I want to think of a hoop. I see a hoop here. So I'm going to think of this disk as a collection of hoops. So that may sound strange to you, but it sounds good, I think. So here's specifically what we mean. Here's one hoop, okay? It's an element of mass. It has a thickness dr. Right? And I know the moment of inertia of that hoop. It's 1/2 the mass of the hoop times the square of little r. All right? So, what's the mass of this hoop here? Well, it's a differential because we're taking a differential thickness here. And it's going to be the mass per unit area. Now it's natural to use the mass per unit area. Previously it was natural to use the mass per unit length. Now we want to use the mass per unit area. And that's often called sigma. It's going, because the disk is uniform, it's going to be the total mass divided by the total area. The total mass is m. The area of this is pi capital R squared. So the reason I'm doing this is because now I can write down what the mass of this elemental hoop is. It's the mass per unit area times the area that you see here of the hoop. And what's that? That's the circumference times the thickness. So there's the circumference and there's the thickness. Now, once you realize what I just said here, and it probably takes a little getting used to, right? You have to think about it a little bit. Once you see it, the rest is easy. It's just turning a crank, okay? So, here it is. We integrate over all these little elemental hoops, which is each hoop contributes r squared times its mass. So we substitute for what the mass of the hoop is in here. And now we have, this is calculus. The integral, everybody can integrate this. The integral of r cubed is going to be 1/4 r to the 4th. And I evaluate it, and I get this. And again, nobody remembers this. You want to now substitute what sigma is. Remember, sigma is the total mass. We did a similar thing with the rod, right? You substitute it in, simplify, and you get something that you will not be able to forget after taking this class, because we're going to use this so much. It's 1/2 the mass times the square of the radius. The moment of inertia of a disk about its axis of symmetry is 1/2 the mass times the radius of the disk. It turns out to be a nice simple factor here. Why is there a factor there? Why isn't it for a hoop of the same mass and the same radius, we have half the inertia here? Why is that? A hoop is mr squared, right? That follows immediately from the definition. I should have written that, there we go. Okay, now we have 1/2. Why is it less? This is a simple question.
Because the mass is spread out.
Yeah, the mass is, you can imagine starting off with a hoop. To get to the disk, we got to migrate some of that mass. We got to migrate the mass towards the center, spread it out towards the center. We're clearly going to be reducing the moment of inertia, and it just turns out here that it's a very simple answer. It happens to be 1/2. I don't know if anybody has a physical argument for that, but the integration here shows that it's simply 1/2. But we would definitely expect a number here between 0 and 1. This coefficient here has to be between 0 and 1. It's got to be. And it turns out to be 1/2. Easy to remember. Oh, here's something. Where's the thickness? There's going to be some thickness here. How come that's not in the answer, in our expression here? Yeah, m is in there. R is in there. What about h? Call that little h. How come h is not in there?
If you reduce r, but keep m the same, h will increase. So you only need m and r to define the
Huh? Yeah, let's look at it from a different point of view. Suppose I took this disk and I imagined spreading it out. All I'm doing, I'm just spreading it out. I'm keeping r the same, m the same. It's density. Mitch was fixing the density. Okay, let's not worry about that. Let's just imagine spreading. How's the moment of inertia going to change? What if this is a cylinder instead of a disk? Something like this. What's the moment of inertia going to be about the axis? It's going to be the same, right? And the reason is, every little element of mass, its distance to the axis has not changed. When I spread it out like this, now this is not a practical thing. And this is what Mitch was thinking. If you tried to do this, its radius is going to go down, right? If I take something and stretch it, it's going to compress. But that's because it's trying to keep the density the same, okay? But this is just this is a Gedanken thing, experiment here, okay? This is just a thought experiment. If I imagine spreading this out, every little bit of mass is going to stay the same distance to the axis. So the moment of inertia can't change. That's why h is not in here. That's why it's not in there, this height here. So we can, one way of summarizing this is that the moment of inertia of this, what we think of as a disk here, is the same for the same mass and the same radius. It's going to be the same if you have something that we would normally call a cylinder, right? Of a mass here and a radius here. The moment of inertia, the rotational inertia presented by this object here is going to be the same as the disk. Okay, any questions or comments? Okay, so another, obviously, since we're headed towards rolling objects in the next chapter, we want to deal with spheres, okay? Now, I want to emphasize something here, that this is a uniform, there's two types of spheres that people typically deal with. There's a uniform solid sphere, like a billiard ball, and then there's a spherical shell, which is, it could be thin. And we have that. We have a lot in the demo lab. It's one of the reasons that it looks so messy, and is messy. Yeah. So, I just want to make a note. I might bring that up. I normally don't show that. That's done for an acoustics demonstration, because it has a hole in it. We made a hole in it, and then you blow across the hole and you hear a tone, right? It's like this. Do kids still do this? It's really annoying, right? And I remember when I was a kid, and it drove them crazy. I think the elementary school we went to, I think they like passed a law saying you can't do that. They did stuff like that back then. I don't know if they can do that anymore. There might be legal problems. But I think they said, you can't do that anymore, and you can't do any gestures that the Three Stooges do. Now, I don't know if you guys ever seen the old Three Stooges movie. Yeah, they had these gestures, and that was so popular. And they said, no, that's it. We have a law now. You can't do that. And we said, okay, we just did what we were told. Duck and cover. We ducked and covered. Okay. So, how do we find the moment of inertia of a uniform solid sphere about a diameter here? About an axis going through a diameter. Okay. Well, it turns out I think probably the easiest way to do it is to imagine that we have a collection of hoops again, but the hoops are going to have a varying height. I see a hoop here. Then the next one in it's a little higher. It's going to cause their mass. It takes a little bit of effort. I think, I looked in the book, it's not in the text. It's probably a homework problem in the back of the chapter, but I don't think we're going to do it, okay? If anybody gets interested in how this is done, you'll find the derivation somewhere on the internet. And you can always come by and talk to me about it. But here's the answer. It's 2/5 mr squared. 2/5. So you'll notice here, what is it in comparison to a disk of the same mass and the same radius? Remember the disk? 1/2 mr squared? 2/5 is less than 1/2. So can we qualitatively explain that? If I took this and Gedanken compressed this, okay? I'm imagining compressing this down with each mass element staying the same distance to the axis, okay? Do I get a disk? A uniform disk?
Oh, it's loaded, is it?
It's greater density towards the center. So that's going to lower. And look at that. That 2/5 is less than 2.5. 2/5 is less than 1/2. What's interesting is it's not that much less, but that's qualitative. It's in qualitative agreement. Okay, enough moments of inertia right now. Specific cases. That's going to get us a lot of mileage knowing those. The next thing is this theorem, and it's got a great name. It's called the parallel axis theorem. Which it's called that because it has to do with parallel axes, and that's reminding you. Okay, whoever, I don't know what the history of this is, but I think the name is some instructor got tired of students misusing it, so they said the students need to understand that this applies only to parallel axes. So that's probably why. That's maybe what happened there. So here's the idea. Here's the theorem. It says the moment of inertia, you have a rigid body, and you take any axis, anywhere, okay? Is there anything wrong with taking an axis over here? No, we just imagine we have some massless rods connecting this. There's nothing right, so it can be anywhere. The parallel axis theorem relates the moment of inertia about any axis here to a parallel axis going through the center of mass. And here it is. And we're going to prove it in general for any rigid body. And it's an easy proof, as you'll see. I want to point something out first, though. Oh, this is useful because, like the rod, well, the first thing we're going to apply this to is the rod. We calculated the moment of inertia about here, about the center, right? It's 1/12 the mass times the square of the length. What's the moment of inertia about here? That'll come up in a lot of problems. Well, if we know the moment of inertia here, we can get the moment of inertia about this parallel axis over here, right? So it's useful for that reason. It's also useful because it's telling you something here. Suppose you want to find an axis among all possible parallel axes, the axis that minimizes the moment of inertia. Which axis is going to minimize the moment of inertia of a whole collection of parallel axes? How do I minimize this? Well, I take h equals to 0. H is the distance between the two parallel axes. So in other words, of all possible, you have a bunch of parallel axes, and you can define any family you want, okay, just as long as they're all parallel. The axis that has the minimum moment of inertia is going to be the one through the center of mass, which kind of makes sense. You know, the farther, if I get over here, I'm going to have a big moment of inertia, right, because I got a big distance here. And the axis that minimizes it among all the parallel ones here is the one passing through the center of mass. So here's the proof. Now, this is probably going to look, this is analytical, okay? It's the advantage of it is it applies to any rigid body. All right, so we'll just use the summation notation. We'll use that. You know, it applies to any. You know, it doesn't have to be a. This is true instantaneously. It doesn't have to be a rigid body. Is that right? Wow, the application is overwhelming for rigid bodies, but I think this is more general than that. It's like any system of particles. Okay, so here's the definition of the moment of inertia, which we derived for a rigid body. So I guess I have to say, yeah, the usefulness of this is for rigid bodies, because this is the moment of inertia for a rigid body. Everything has to be locked in place. Remember, V is equal to omega r? If you've got things going their own merry ways, this is not just going to be meaningless, not going to be useful. Okay, so here it is. Now, the trick here is this is the relevant distance for this little mi here. We want to represent it as a vector sum, each little ri here, this vector, as this vector to the center of mass plus this one. That's the trick here. So we get rid of r vector in terms of h and I. Now h here is just it doesn't depend upon what the mass element, it's just this fixed vector here from our axis to the center of mass. Now you can square this and you get three terms. You get the h squared term, first of all, because that's constant, it comes outside the sum, and we just have the total mass times h squared. The third term, similarly, is the mass times di squared. We can't take di out because it depends, okay, on I. What about this middle term here? Does this look familiar? This is the sum of the moments of all the masses about the center of mass. So remember what this equals to? The sum of the moments is the total mass times the vector to the center of mass. So if I'm at the center of mass, because this D is in the frame of reference where our origin is the center of mass, this has to be, this specifies the balance. This is the balance point. So this sum has to, the sum of the moments has to be 0. It's got to be 0 when you have the center of mass here. Because we have a theorem that says that the sum of the moments is the total mass times the r vector to the center of mass. And if we're at the center of mass, that r vector is 0. So this term goes away. We get this, and then we just prove the theorem. You just have to move things around a little bit. Right, you just have to move this over here, and you get this. So it's actually easy to prove in general. So we're going to look at a couple of applications of this. Here's, as promised, here's the rod, okay? And most people, and somewhat including me, don't remember this 1/12 ml squared, because this is like a weird number, 12. However, if we ask what the moment of inertia is about the axis about the end, and we use the parallel axis theorem, I about the end is I center mass plus the total mass times the distance to the center of mass, which is L over 2. What's 1/12 plus 1/4? It happens to be 1/3. So this is what people usually remember for the moment of inertia. They remember the moment of inertia about the end of a rod. And that's often, in applications that often comes up. So usually, people including me memorize this just naturally. If you want to find the moment of inertia about the center of mass, what do? Well, you just, if we know the moment of inertia, see, this tells us what the moment of inertia is if we know the center of mass. If we know this about some axis, then we can find the moment of inertia about the center of mass, right? It's just algebra. They call that algebra. So we can look at it from, turn the tables on us, look at it two different ways. So most people remember this is 1/3, and then if they need it here, they can use the parallel axis theorem to get it. Now, just a little word of warning here. Obviously, if I have an object, it's going to have a center of mass. So if I want to find the moment of inertia, shouldn't I just take its total mass times its distance to the center of mass? Let's call it x here. Squared. We have all these center of mass formulas, right? This sounds good. The total moment of inertia of a body is the same if you imagine its mass to be concentrated at the center of mass. It's bullshit. It's not right. Is it? What would it take? Look at this. Look at the center. This. It has a moment of inertia. If I imagine all the mass to be concentrated at the center of mass, you get 0, right? So this is not true. It's one of those, you got to be careful, even though the center mass has a lot of properties, and it sounds good. The center mass is the same if you imagine. It's not right. It's obviously not true. So that's just a little word of warning there. Okay, so there's a demo here, okay? And it involves oscillatory motion, something we're not going to be able to do in this class. But it's still worthwhile to see this demo, I think. So this object, this is a kind of pendulum. It has a frequency there, or a period, the time for one cycle, right? And what we don't have time to derive is the fact that the period here is given by, it's in the notes there, the square root of the moment of inertia times divided by the total mass times g times the distance to the center of mass. Okay? So this has some total mass. It's what's the distance to the center of mass? Where's the center of mass? Right in the center, geometric center here. And it's got some moment of inertia about that axis. And you can calculate it, but we're not going to do that. Okay? But the point of this demo is, I've got an identical plate here, but I'm going to put it at 90 degrees. Okay, this is also pendulum. What should be the, how do those periods, which period's going to be bigger? Any guesses? I heard something.
They gotta be the same, that's what he's saying.
Why are they the same?
Because the mass is the same. Center of mass.
Oh, the moment of inertia depends upon the distribution of the mass. So I see, whoa, this thing's this is called a librator, right? That's important for the Tacoma Narrows Bridge collapse. I keep working on that. when I get a chance. So it looks like the distribution of the mass are about this, it looks like they're going to be different moments of inertia. However, what does the parallel axis theorem tell us? Okay, the masses are the same. What about the distances to the center of mass? Same, but it looks like the moments of inertia are going to be different. However, the parallel axis theorem tells us that the moment of inertia about here is the moment of inertia about the center plus the total mass times the square of that distance. So what do I get over here? The same. So these should have the same period. So let me see if I can do that here. I'm going to try to release them from rest. A little bit of phase there, but you see they're the same? So this is actually, you can think of this as a demonstration of the parallel axis theorem. Somebody published that, believe it or not, in an educational journal. I know because I was the one who published it. Okay. All right. Short article. I looked into that because I wanted to see. There are some really, it got murky. So this thing about the monkey hunter, I checked into that. It's very short, but you'll find really short things. There are a lot of times just notes that somebody wrote about some other paper, so I couldn't really claim it, so I dropped it. I usually follow up on these things. But, yeah, so forget the Guinness Book of World Records. That's gonna. All right, so we're setting the stage for dynamics. We've got to do one more thing here before we get into it, and that's to deal with torque. Torque, you've all heard of that, and it's the rotational analog of force. We're headed towards an F equals ma type description. And instead of m, what are we going to have? Take a wild guess. Moment of inertia, right? And instead of A, anybody?
Omega.
Alpha, right? D omega dt. So we're headed towards, and so what's the analog of force? Well, that's what torque. So we're headed towards, torque is equal to the moment of inertia times the angular acceleration, which is d omega dt. That's where we're headed, okay? So we're going to talk about torque now. So here's a fixed axis of rotation. Here's a body. A force, an arbitrary force, is applied at some arbitrary point off axis here. So this is a force here. We can resolve the force into two components, a radial component and a tangential component. Somebody is making sure this axis is not moving. Okay, it's attached to some bearings, attached to the Earth. Okay, what influence does FR have on the rotational motion? I'm looking for one word here, starts with Z. Zero. This is not going to influence the rotational motion. You have an object like this, you exert a force like this, nothing's going to happen. Something has to prevent, it's going to be balanced by whatever this axle here, whatever it's rooted in, okay, whatever it's anchored to. So this is irrelevant. That's interesting. What's important is the tangential part, but that's not only what's important. See this distance here? What if I applied this tangential force, but I doubled the distance? What's going to happen to the angular acceleration? And you've all experienced something like this. It's going to increase. It's going to, in fact, double. Okay? So our definition of the appropriate definition here, and the only reason it's known to be appropriate because people played around with it and looked in looked back and say, okay, that's what, in retrospect, looking back, this is what you want to define it as. The torque is the tangential component times that distance right there. That's the torque. We can put it in terms of the total force if we multiply by the sine of theta, because the tangential component here, this is the same as that, and you can see that it's F times the sine of theta. So that's our definition of the torque. There's an alternative definition that is sometimes useful. So our current definition is you take this component of the force, right, and multiply by this. Here's another way of looking at it. that's useful. It is useful, and as we will see. Forget this component. Consider your actual full force here, but the distance, the effective distance in regards to rotation is going to be this distance right here. That's called the moment arm, this right here. This is called the moment arm of this force F. So I can look at the torque as this distance times this, the tangential component. I can also look at it as this times the relevant distance, which is this moment arm. They're identical. It's just where you put the sign of theta. There's a sign of theta floating around here. And before we associated the sign of theta with this f of t, now we're associating with the r. This is r times the sine of theta. Now we have to talk about direction here. And the direction, the appropriate direction is, we can use the right-hand rule. So we can actually unify the magnitude and the direction into one nice expression here. It's r cross f. So in this case, where does the torque point? This is r, straight out. And it's going to cause an angular acceleration that is straight out. Okay, let's do a quick example here. So here's a kind of wrench, and somebody is exerting a force near the end here, certain distance from the center, at some angle here, 60 degrees from here. So what's the torque? Well, there's two ways of doing this. We can take the relevant component of the force, which is this tangential component right here. So to get that, I'm going to take f times the sine of theta. That's going to give me this component. That's the relevant component, the tangential component of the force. I multiply by 1/4 of a meter, and I get 32.5 Newton meters. Now another way of doing it is, I admit it's a little stranger, but it is useful, as we'll see, is I can use the full force, but now I got to multiply it by the moment arm. So let's do the calculation that way. What is this distance? Well, do you see the right triangle right here? We know the hypotenuse. We know the angle. We can get this. So the moment arm is r times the sine of theta. It's equal to this. I'm using a lot of extra figures here just so I can get the same answer. You know, exactly the same answer to 3 figures. So this is the moment arm. I now multiply the moment arm by this 150 newtons, and I get the same answer. Okay, so we'll except for this little bit on gravitational torque, we'll get into the rotation. Now we're ready to do the rotation.